Today we're going to start looking at exponential functions. So an exponential function is where you've got x as the exponent. So you may have looked at, we've looked at functions that were, say, y equals x squared. Well, this is different because it's y equals 2 to the x, for example. Example 1 says the exponential function f of x equals 42.2 times 1.56 to the x models the average amount spent, f of x, in dollars at a shopping mall after x hours. Now, I want to point out that exponential functions, it's not just f of x equals b to the x, but it could be some number times b to the x. And in this case, your b to the x is your exponent. The x is on the b. And then the a is just being multiplied. So it says, what is the average amount spent to the nearest dollar after 3 hours at the shopping mall? So we're just going to plug in 3 for x. And when we do this, we have to do, by order of operations, the 1.56 to the third before we multiply by 42.2. And you can put this in your calculator like that. And I'm not going to write out what is 1.56 to the third because it's a really long decimal and I don't want to get rounding error. So we just put it all in our calculator at once, or put the 1.56 to the third in first and then just hit multiply by 42.2. And we should get $160.21 is the average spent after 3 hours at a shopping mall. For example 2, we're going to determine whether the function is linear, exponential, or neither. So a lot of times you might have a scatter plot that looks like it could be linear, but exponential might be a better representation. So for those that are linear, find a linear function that models the data, and for those that are exponential, find an exponential function that models it. So for part A, we've got these points, and we could graph them, but we don't have to. Basically, what we need to do is we need to find the change or the rate of change with these points. So we've got the point -1,6 and 0,2, and we're going to find the change in the y over the change in the x, or basically the slope between those 2 points. So we'd subtract our y's, 2 minus 6, over subtract the x's, 0 minus -1, and we get -4. And you'll see why we're doing this in just a minute. So first we started with these 2 points. Now we're going to go with the next pair. So -2 minus 2 over 1 minus 0 is -4. The next pair would be -6 minus -2 over 2 minus 1. Also -4, and then the last pair, -10 minus -6 over 3 minus 2 is -4. So what we were trying to do here is to see what the rate of change was, and if all the rate of changes are the same, then that means we have a linear function. So since they're all -4, then the function is linear. And we can find a line that passes through these pretty simply. We've already got the slope. It's -4. And the y-intercept is 0, -2. That's where x is 0, y is 2. So B is 2. So if we plug in for y equals mx plus b, then we've got y equals -4x plus 2. For part B, we're going to start out with the same thing. So we've got the change in the y over the change in the x for this first pair. We got 27 minus 81 over 0 minus -1 is -54. And then the next pair, 9 minus 27 over 1 minus 0 is -18. So we can already tell that these are not linear. So what we've got to determine is it exponential? To test for exponential, we take the fraction of the y values. So we're going to start with 27 over 81 in that first pair, and we get 1/3. And this only works, by the way, if our y's are going up evenly. In this case, they're going up by 1, so we have to make sure that they're the same. Then if we look at the next pair, it's 9 over 27 is also 1/3. The next pair, 3 over 9, is also 1/3. So what that means is that our growth factor, or B, is 1/3. And that's when we're looking at y equals A times B to the x. Now what is A? A is the y-intercept. And the y-intercept, where x is 0, y is 27. So we plug in y equals 27 times 1/3 to the x, and that would be our exponential function. For the next couple of examples, let's graph some of these. So y equals 3 to the x. If we pick some points, I'm going to go -2, -1, 0, 1, and 2. Then we just plug in. So 3 to the -2 power, that is 1 over 3 squared, or 1/9. Three to the -1 is 1 over 3. 3 to the 0th, anything to the 0th power is 1. 3 to the first power is just 3. And 3 squared is 9. And then we'll come over here and graph those. So -2, 1/9 are very, very close to 0 there. -1, 1/3. 0, 1. 1, 3. And 2, 9. And connect the dots. It's going to keep on going up, more and more vertical from the 0.29, and it's going to keep going to the left, getting closer and closer to 0 as we move to -infinity. And there's a picture of it. For an exponential function, the domain is the set of all real numbers. It continues to the left forever and to the right. There's no x-intercepts if you've just got y equals 3 to the x or y equals 2 to the x. If you're not negative or have a different y-intercept or something like that. The x-axis is a horizontal asymptote. So like y equals 3 to the x, you could see that the x-axis is a horizontal asymptote. If b is greater than 1, then it's increasing. And if it's a fraction or a decimal, then it's decreasing like this. And the function is smooth and continuous. And if you'll notice, if it's just 3 to the x or 2 to the x or negative 5 to the x, if there's not another number being multiplied, then our y-intercept is at 1. For example 4, we want to use the graph of 3 to the x to obtain the graph of 3 to the x minus 1. Now remember the x minus 1, when it's in the exponent form there, then that means we're moving right or left. And since it's minus 1, then we're going to the right 1 unit. So every point, like this point 0, 1, is going to move to the right. And then let's see, where's it crossing again? Not till up at 2, 9. And it's going to move to the right. And so if we find a point, say right here, that's going to move to the right one. And so now I think we can draw a fairly good graph of y equals 3 to the x minus 1. Everything just moved over to the right one. What is base e? E is just a number, and it's a number found by this 1 plus 1 over n to the nth power. And as n gets larger and larger, e gets closer and closer to 2.7182827, and it keeps going. And so this number is similar to pi, but in the fact that pi is a number, e is a number, but it does, I believe it does repeat in there a little bit. It's called the natural base or the natural exponential function. For example 5, the exponential function 1066 e to the 0.42x models the gray wolf population of the western Great Lakes X years after 1978. Project the gray wolf's population in the year 2012. So we need to first of all figure out, well, what's X in 2012? It would be 2012 minus 1978, because 1978 would have been the 0th year. So X will be 34. And we're going to take 34 and plug it into our function. When you put that in your calculator, you might want to go ahead and find what is 0.042 times 34. It is 1.428. And then you just put it in your calculator. 1,066 times e to the 1.428. And we should get 445.59. Now you can't have 0.59 of a wolf. So what we usually do when you're talking about animals or people, we round down. So that would be 4,445 wolves. Now some math programs will round up, and hopefully it will tell you that in the problem. But typically, because you can't have 0.59 of a wolf, you can't have part of a wolf, then it wouldn't really make sense to round up. It makes more sense to round down. For example 6, we're going to use the graph of y equals e to the x, that's graphed here in gray, to obtain the graph of 1 minus e to the x. Now, to do this, the easiest thing would be to rewrite it with the e to the x coming first. So let's say negative e to the x plus 1. And so we know that the plus 1 is telling us to go up 1. And we know that the negative is telling us to reflect over the x-axis. And you can look back in your transformations notes for that if you need to. Okay? So let's first start with reflecting it over the x-axis. So we'd have a point here, and it's going close to 0 still. And let's see, it's not any exact points in here. That one's pretty close to 7. So let's go pretty close to the left there of negative 2, 7. And then the plus 1 says to move it up 1. So everything's going to move up 1. And our y-asymptote is then going to be the line y equals 1 instead of y equals 0, because the y-asymptote moved up 1 also. And so that red one is what 1 minus e to the x would look like. And excuse the kitty, he thinks he's going out again, and it's nighttime, and he's not going out. We don't have wolves here, but we have coyotes. Okay. Formulas for compound interest. This is something that we look at when we are talking about exponential functions, because compounding or interest is, when it compounds, it is generated with an exponential function. For interest that's compounded n times per year, and n times per year meaning if it's monthly, the n would be 12. If it's compounded quarterly, then the n would be 4. If the interest is compounded daily, n would be 365, and so forth. P is the principal, the initial amount of the loan or the deposit, or whatever you're dealing with. R is the interest rate changed to a decimal. And T is time. And then for continuous compounding, then it's A equals PE. There's where our E comes in to the RT. We don't have to deal with N there. For example 7, we're going to look at a sum of $10,000 invested at an annual rate of 8%. Find the balance in the account after 5 years, subject to quarterly compounding. So we're looking at the function a equals p times 1 plus r over n to the nt, and we're going to plug in. So we started with $10,000. Then we have 1 plus, the rate is 8%, so that's 0.08, changing it to a decimal. We're compounded quarterly, so n is 4. And t, it says 5 years, so we're going to multiply by 5. We can go ahead and put 1 plus 0.08 divided by 4 into our calculator. You get 1.02, and 4 times 5 is 20. So with quarterly compounding after 5 years, you would have $14,859.47, which would be lovely if you could actually go to the bank and get 8% interest. Does not happen. Well, unless you're getting a loan, and then, yeah, they're going to charge you that. Okay. And then for part B, we're going to do the same thing, but with continuous compounding. So again, $10,000 at 8% interest for 5 years. I'm trying to use the same colors. And we're using continuous compounding. So this time we're using A equals PE to the RT. The principal is still 10,000. R is 0.08. And T was 5 years. You can, if you like, go ahead and multiply 0.08 times 5. It gives you 0.4. And we end up with $14,918.25. So you can see here, if you're investing, you want continuous compounding because you get just a little bit more money. And then for example 8, we're going to look at an example of an exponential equation. And we'll look at more of these in the future. But what we've got here is it says 9 to the 2x minus 5 and 27 to the x. There's a rule that says if you've got b to the x equals b to the y, then you can say x is equal to y. So if your bases are the same, then you can say that your exponents are the same. Unfortunately, in this case, the bases are not the same. You've got 9 and 27. But you can get the bases the same because both 9 and 27 are, how do we say it, can have a base of 3. So 9 is 3 squared, and 27 is 3 cubed. So we can multiply through our exponent there. 2 has to be distributed, so we get 4x minus 10, and then 3 to the 3x, and now our bases are the same. We can set 4x minus 10 equals to 3x and solve it just like you always have. I'm going to subtract 3x from both sides and add 10 to both sides, and x is 10. And that concludes our section on exponential functions.